Hello, in this lecture we will find out the area of the green shape. In the drawing we have a circle. We know that the radius of this circle r equals to 2. R equals to 2 units. And inside this circle we have peripheral angle ACB that is equal to 70 degrees in its side. And we also have here the common extreme point P. From the common extreme point P, we have two tangents to this circle. Tangent PA, that is tangent to this circle here at point A, and tangent PB, that is tangent to this circle at point B. Our mission is to find out the area of this green shape. Okay. So, first of all, we'll join points O and B together by a straight line. Point O is of course the center of the circle. So point O is the center of the circle, point B is the point on the circle itself, therefore OB is the radius of this circle, R, that is equal to 2 units according to what is given as the question. So we can implement here rule 1. I'll repeat quickly on rule 1. According to rule 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle, and also we have, this is tangent AB, that is tangent to this circle here at point M. Point M is the point of tendency of tangent AB with this circle, and we have the radius OM that is equal to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees. We can actually implement rule 1 in our drawing. Why? Because in our drawing we have the radius OB that is drawn to point B, that is the point of tendency of tangent PB with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees. Likewise, we have the radius OA that is drawn to point A, that is the point of tendency of tangent PA with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PA will be perpendicular to the radius AO. If PA is perpendicular to AO, it means that this angle equals to 90 degrees. In the next step, I will present to you a new rule, and we will implement the new rule in our drawing. According to the new rule, that is actually rule 13, a central angle is twice as large as the peripheral angle that is subtended on the same arc. Repeat again rule 13. According to rule 13, a central angle is twice as large as the peripheral angle subtended on the same arc. So in the drawing we have a circle. Inside this circle we have the peripheral angle ACB. Peripheral angle ACB is equal to theta in its size and is subtended on RKB. Again, peripheral angle ACB is subtended on RKB. In addition, we have also in this drawing the central angle AOB, this is the central angle AOB that is subtended on the same arc, RKB. And because of the fact that the central angle AOB is subtended on the same arc as the peripheral angle ACB, it must be twice as large as the peripheral angle as ACB. So peripheral angle ACB equals to theta, therefore the central angle AOB that is subtended on the same arc will be equal to 2 theta. Okay, so we can actually implement Rule 13 in our drawing. Why? Because in our drawing we have peripheral angle ACB. This is peripheral angle ACB. This is equal to 70 degrees in its size. And peripheral angle ACB is subtended on RKB. Again, peripheral angle ACB is subtended on this arc RKB. And we have the central angle AOB. The central angle AOB, this is the central angle AOB that is subtended on the same arc RKB. And therefore, according to Rule 13, the central angle AOB must be twice as large as the peripheral angle ACB that is subtended on the same arc RKB. And because of the fact that peripheral angle ACB equals to 70 degrees, it means the central angle AOB that is subtended on the same arc RKB must be equal to 70 degrees times 2, that is 140 degrees. According to Rule 13, of course. In the next step, we'll join points P and O together by a straight line. By joining points P and O, we created here two right triangles. The upper right triangle POA and the lower right triangle, triangle POB. So in the next step, we prove that those two right triangles can join to each other. So I write it down. We prove that the upper right triangle, triangle POA, can join to the lower right triangle, triangle POB. So why those two right triangles can go into each other? First of all, side AO of the right triangle AOP is equal to side OB to the right of the right triangle, triangle OBP. Why? Because both of them are the radii of this triangle, therefore they are equal to each other. Each side is equal to 2 units. So I write it down. Side OA of the right triangle AOP is equal to side OB of the right triangle OBP. OA equals to OB, they are both on the area of the circle, and the radius of the circle equals to 2 units according to what is given as the question. In addition, the side OP is a common side that belongs to both triangles, so we can write down that OP equals to itself. Side OP equals to itself is a common side that belongs to both triangles. So OP equals to OP is a common side that belongs to both triangles. And finally, side AP of the right triangle AOP is equal to side BP of the right triangle OBP. Or PA equals to PB. PA equals to PB according to Rule 2. I remind you what is on rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. So in the drawing we have a circle, and we also have here the common external point, point P. From the common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule, rule 2, they are equal to each other. That is to say, the length of PA is equal to the length of tangent PB. PA equals to PB according to rule 2. So actually implement rule 2 in our drawing. Well, because in our drawing we have the common external point, point A. From the common external point, we have the common external point, point P. From the common external point, point P, we have two tangents to the circle, tangent PA and tangent PB. And according to rule 2, PA equals to PB. Yeah, PA equals to PB according to rule 2. So actually proved that all the three sides of the right upper triangle AOP are correspondingly equal to all the three sides of the right triangle BOP. Therefore, those two right triangles can move into each other according to side rule. So I write it down. The right upper triangle, triangle POA, is congruent. This is the sign of congruent to the right lower triangle, triangle POB. According to side rule. And from the fact that those two right triangles can go into each other, we will derive that those two angles are also equal to each other. Okay? According to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding angles must be also equal to each other. This is angle AOP. And it is equal to this angle and triangle BOP. This is actually angle BOP. Okay, again, we found out that angle AOP equals to angle BOP. So if we define one of those two angles as alpha, then the other angle must be also equal to alpha because they are equal to each other. If we define this angle as alpha, then the other angle must be also equal to alpha because they are equal to each other. So alpha plus alpha equals to 140 degrees. Here, alpha plus alpha equals to 140 degrees. Okay. Alpha plus alpha equals to 140 degrees. That is to say 2 alpha equals to 140 degrees. We divide this equation by 2. And we get that the missing angle alpha equals to 140 degrees over 2 is 70 degrees. So actually this is angle alpha that is equal to 70 degrees in its size. And this is also angle alpha that is equal to 70 degrees. In the next step, we will focus on the right upper triangle, triangle AOP. On the right upper triangle, triangle AOP. This side triangle AOP. What is the value of tangent 70 degrees? Tangent 70 degrees equals to AP over AO. Repeat again. The right triangle, right upper triangle AOP, tangent 70 degrees equals to AP over AO. AP is the missing side, so we'll leave it as it is. So it is AP over AO. AO is the radius of this circle that is equal to 2, so we'll substitute AO by 2. So tangent 70 degrees equals to AP over 2. The value of tangent 70 degrees is 2.75. This equals to AP over 2. Here we'll multiply this equation by 2, and finally we'll get that AP equals to 2.75 times 2, that is 5.5 units. So in conclusion, found out that AP equals to 5.5 units in its length. This is side AP, this equals to 5.5 units. Okay. We can repeat on the same process and we find out that BP is also equals to 5.5 units, but we actually don't need to do it. What is the area of the green shape? From the drawing, it is very easy to see that the area of this green shape is equals to the area of the right upper triangle, triangle AOP, plus the area of the lower right triangle, triangle BOP, so actually the sum of the areas of those two right triangles will give us the area of quadrilateral AOBP, and when we will subtract from the area of quadrilateral AOBP the area of this sector, sector AOB, we will get the area of this green shape. Okay. Repeat again. We actually found out that the area of the green shape equals to the area of the upper right triangle AOP plus the area of the lower right triangle BOP. The sum of those two areas will give us the area of quadrilateral AOBP, and when we will subtract from the area of quadrilateral AOBP the area of this sector, sector AOB, we'll get exactly the area of this green shape. Again, it is the sum of the areas of two right triangles minus the area of this sector, sector AOB. So this is how we write down the area of sector AOB. The rounded line above AOB, it means sector. Okay, so this expression means the area of sector AOB. The square bracket is the same for the area, and the rounded line above AOB is the same for a sector. Okay, so what is a sector? A sector is a portion of a circle or part of a circle. We have a circle, and the green shape AOB is a sector. The sector consists of two legs. The first leg is AO and the second leg is BO. Both those two legs are the radii of this circle. They are equal to R, and therefore they are equal to each other. So the green sector AOB consists of those two legs AO and BO and the arc AB. Okay, so you can look at a sector as a pizza slice. Okay, and this is angle theta, that is the angle between the legs AO and BO of this green sector AOB. So what is the area of this sector AOB? The area of sector AOB equals to the area of the circle that contains the sector, that is actually pi r squared, because the radius is r. So it is the area of the circle that contains the sector, that is pi r squared, times theta, that is the angle between the legs of this sector, over 360 degrees. Repeat again, the area of this sector, the green sector AOB, equals to the area of the circle that contains the sector, that is pi r squared, times the angle between the legs of this sector, that is theta, over 360 degrees. Okay. So we have to find out the area of the right triangle AOP, and then we will add the area of the right triangle AOB to the area of the right triangle BOP, and then we subtract from the sum of those two areas the area of sector AOB. But because of the fact that we have already found out that those two right triangles can go into each other, they have also the same areas. They have also the same areas because they can go into each other. So we will just multiply the area of the upper right triangles by 2, and the result will be the area of those two right triangles. So here, if we substitute the area of the right triangle BOP by the area of triangle AOP, we get that the area of the green shape in total will be equal to the area of the upper right triangle AOP, and we'll substitute the area of the lower triangle BOP by the area of the upper right triangle BOP, so it is the area of the upper right triangle AOP minus the area of sector AOB. So the area of the right triangle AOP plus the area of the right triangle AOP is 2 times the area of the right triangle AOP. Minus the area of sector AOB. So first of all, we find out the area of the upper right triangle AOP, and we multiply it by 2, and the result will be the area of this quadrilateral AOBP. So what is the area of the right upper triangle, triangle AOP. The area of this right triangle, triangle AOP. First of all, the area of any triangle equals to the base of the triangle times the height to the base over 2. So we take the base of this right triangle, triangle AOP as AO times the height. The height is AP, why? Because AP creates 90 degrees with the base. So the height is AP divided by 2. So AO is 2, it is the radius of this circle that is equal to 2 units in its length, times AP. We already found out that the length of side AP is 5.5, so it is 2 times 5.5 divided by 2. So here we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled, and we have to only with 5.5. So we found out that the area of the upper right triangle, triangle AOP is equal to 5.5 square units. And we have to multiply the area of triangle AOP, that is 5.5 by 2. 5.5 times 2 is 11. So 11 square units is the area of quadrangle AOBP. We have to subtract from this quadrangle AOP, the area of this quadrangle AOBP, that is 11, the area of this sector AOB. So it is 11 minus the area, 11 square units minus the area of sector AOB. In the next step, we'll find out the area of this sector AOB. So what is the area of sector AOB? The area of sector AOB equals to the area of this circle that contains sector AOB. The area of this circle equals to pi r square times the angle between the legs of this sector AOB. This angle equals to 140 degrees over 360 degrees. The radius of this circle r equals to 2, therefore r square is 2 square. That is 4. So pi r square is 4 pi. 4 pi. And we have to multiply the area of the circle by 440 degrees over 360 degrees. So the value of this expression in total is equal to 4.888 square units. So actually found out that the area of sector AOB is equal to 4.888 square units. So the area of the green shape equals to the area of this quadrangle AOBP, that is equals to 11 square units, minus the area of sector AOB that we just right now found out, that is equals to 4.888 square units. So I write it down. The area of the green shape is equals to the area of this quadrilateral AOBP. This is actually the sum of the areas of those two right angles, and we already found out that the sum of the areas of those two right angles, that is actually also the area of the quadrilateral AOBP, is equals to 11 square units, minus the area of sector AOB that we just right now found out that it is 4.888 square units. So 11 minus 4.888 is 6.111 square units. So in conclusion, found out that the area of this green shape is equals to 6.111 square units. And that is the answer to the question. In the next step, I will summarize the lecture. In this lecture, we found out the area of this green shape. So in the drawing, we have a circle. We know that the radius of this circle r equals to 2. Inside this circle, we have the peripheral angle ACB that is equal to 70 degrees in its size. In addition, we also have in this drawing the common extreme point P. From the common extreme point P, we have two tangents to this circle, tangent PA and tangent PB. Tangent PA is tangent to this circle here at point A, tangent PB is tangent to this circle here at point B. Our mission is to find out the area of this green shape. Okay. Point O is of course the center of this circle. We join points O and B together by straight line. So point O is the center of the circle, point B is the point of the circle itself. This is exactly the definition of a radius. Therefore, line segment OB is the radius of this circle, that is equal to 2 units. Here we implemented rule 1. We have the radius OB that is drawn to point B, that is the point of tendency of tangent PB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees, according to rule 1. Likewise, according to the same rule 1, because of the fact that we have here the radius OA that is drawn to point A, that is the point of tendency of tangent PA with this circle, therefore tangent PA will be perpendicular to the radius AO. If PA is perpendicular to AO, it means that this angle equals to 90 degrees according to rule 1. In the next step, I actually presented to you a new rule, that is rule 13, and we implemented rule 13 in our drawing. According to rule 13, a central angle is twice as large as the peripheral angle that is subtended on the same arc. I'll repeat again on rule 13. A central angle is twice as large as the peripheral angle subtended on the same arc. So in the drawing we have a circle. Inside this circle we have the peripheral angle ACB that is equal to theta degrees in its size, and this peripheral angle ACB is subtended on arc AB. And we also have the central angle AOB. This is the central angle AOB that is subtended on the same arc AB. And therefore, according to this rule 13, the central angle that is subtended on the same arc as the peripheral angle ACB, it will be twice as large as the peripheral angle ACB. It's because of the fact that peripheral angle ACB equals to theta, therefore the central angle AOB must be equal to 2 theta. Okay, it is twice as long as this peripheral angle. So we can actually implement rule 13 in our drawing. Why? Because in our drawing we have peripheral angle ACB is equal to 70 degrees in its side, and this peripheral angle ACB is subtended on arc AB. And we also have the central angle AOB is subtended exactly on the same arc AB. Therefore, the central angle AOB must be twice as large as this peripheral angle ACB. So the peripheral angle ACB equals to 70 degrees. Therefore, the central angle must be equal to 70 degrees times 2, that is 140 degrees. In conclusion, we found out that this central angle AOB equals to 140 degrees in its size. In the next step, we joined points P and O together by straight line. By joining points P and O, we created two right triangles, the right triangle AOP, the upper right triangle AOP, and the lower right triangle BOP. In the next step, we actually proved that those two right triangles can go into each other. So why those two right triangles can go into each other? First of all, side AO of the right triangle AOP is equal to side OB of the lower right triangle BOP. Because of the fact that both those two sides are the radii of the circle, they are equal to each other. Repeat again. Side AO of the right upper triangle equals to side BO of the right lower triangle POB. They are both the radii of the circle, therefore they are equal to each other. Each side equals to 2. In addition, we have this side OP is a common side that belongs to both triangles, so I can write down that side OP equals to itself as a common side that belongs to both triangles. Again, OP equals to OP as a common side. And finally, side AP of the upper right triangle equals to side BP of the right lower triangle BOP according to rule 2. Okay, repeat again on rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. So in the drawing we have a circle and we have the common external point, point P. From the common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. We implemented rule 2 in our drawing. We have here in our drawing we have the common external point, point P. From the common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to rule 2, they are equal to each other. That is to say, PA equals to PB. PA, side PA of the upper right triangle AOP equals to side PB of the right lower triangle POB, according to rule 2. So actually proved that all the three sides of the right upper triangle AOP are correspondingly equal to all the three sides of this right lower triangle BOP. Therefore, those two right triangles can go into each other according to side rule. Okay, the right upper triangle AOP is congruent. This is the sign of congruent to the lower right triangle POB according to side rule. And from the fact that those two right triangles can go into each other, we will conclude that those two angles must be also equal to each other according to the rule that corresponding angles and congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding angles must be also equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha because they are equal to each other. So alpha plus alpha in total, the sum of those two angles must be equal to 180 degrees, as you can see in the drawing. So we found out that alpha plus alpha equals to 140 degrees. That is to say 2 alpha equals to 140 degrees. We divided this equation by 2 and finally found out that the missing angle alpha equals to 70 degrees. So this is angle alpha that is equals to 70 degrees, and this is also angle alpha, angle AOP is angle alpha that is also equals to 70 degrees in its size. Then we focused on the right upper triangle, triangle AOP. In the right upper triangle, triangle AOP, tangle 70 degrees equals to AP over AO. Again, tangle 70 degrees equals to AP over AO. In the right triangle AOP, tangle 70 degrees equals to AP over AO. AP is the missing side, so we leave it as it is, over AO. AO is the radius of the circle that is equal to 2, so we substitute AO by 2. In conclusion, found out that tangle 70 degrees equals to AP over 2. Tangent 70 degrees equals to 2.75, so 2.75 equals to AP over 2. We multiply this equation by 2 and finally found out that AP equals to 2 times 2.75. That is actually equals to 5.5. In conclusion, found out that AP equals to 5.5 units in itself. Side AP equals to 5.5 units. I repeat again that our mission is to find out the area of this green shape. So what is the area of this green shape? From the moment it is very easy to see that the area of this green shape equals to the area of the upper right triangle AOP plus the area of the lower right triangle BOP. So the sum of the areas of those two right triangles will give us the area of this quadrilateral AOBP. And after we subtract from the area of quadrilateral AOBP the area of this sector AOB, we get exactly the area of this green shape. Okay, so actually found out that the area of this green shape, the area of the green shape equals to the area of the upper right triangle AOP plus the area of the lower right triangle BOP. The sum of the areas of those two right triangles will give us the area of quadrilateral AOBP. And after we subtract from the area of quadrilateral AOBP the area of sector AOB, we get exactly the area of this green shape. Okay, but because of the fact that we just right now found out that those two right triangles can go into each other, they must have also the same areas. So we can substitute the area of this right triangle AOB by the area of this right triangle AOP because they have the same areas. Okay, so here we substitute the area of this right triangle BOP by the area of the right triangle AOP, the upper right triangle AOP, and therefore we found out that the area of the green shape in total equals to the area of the upper right triangle AOP plus the area of upper right triangle AOP because we substitute the area of the lower right triangle BOP by the area of the upper triangle AOP, and then we subtract from the area of quadrilateral AOBP the area of sector AOB. Okay, because the sum of the areas of those two right triangles will give us the area of quadrilateral AOBP, and after we subtract from the area of this quadrilateral AOBP the area of this sector AOB, we get exactly the area of this green area. Okay, so the area of triangle AOP plus the area of triangle AOP is 2 times the area of triangle AOP minus the area of sector AOB. So what is the area of the right upper triangle AOP? The area of any triangle equals to the base of the triangle times the height to the base over 2. The height must create 90 degrees with the base. So here, the area of this right triangle AOP equals to the base of this triangle that is AO times the height that is AP. Again, the height AP creates 90 degrees with the base AO. So it is AO times AP over 2. Repeat again. The base is AO, the height is AP over 2. AO is the radius of the circle that is equal to 2, and we already found out that the height AP equals to 5.5 units in its length, divided by 2. we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled, and we have to only with 5.5. In conclusion, we found out that the area of the right upper triangle AOP equals to 5.5 units in its area. The area of this upper right triangle AOP equals to 5.5 square units. And we already found out that the area of the green shape equals to 2 times the area of the right upper triangle AOP, that is actually 5.5 square units, minus the area of sector AOB. So 2 times 5.5 is 11, and we have to subtract the area of sector AOB. So what is the area of sector AOB? Repeat again. What is a sector? A sector is part of a circle. We have a circle, the green shape AOB is sector. The sector consists of 2 legs. The first leg is AO and the second leg is BO. Both legs are the radii of the circle. That is equal to R. And the angle between those 2 radii, the arc AB that is between those 2 radii, in total, the 2 legs AO and BO that are the radii of this circle, plus arc AB. In total, this is sector AOB. And angle theta is the angle between the legs AO and BO of this sector, sector AOB. So what is the area of this sector? The area of sector AOB equals to pi r squared, that is the area of this circle that contains the sector, times theta, that is the angle between the sector, over 360 degrees. So in conclusion, found out that the area of sector, any sector of sector AOB equals to the area of the circle that contains the sector times the angle between the legs of the sector over 360 degrees. Okay? So according to the formula, we can find out the area of this sector, sector AOB. So the area of this sector AOB will be equal to the area of the circle that contains the sector, that is actually pi r squared, times the angle between the legs of this sector, that is 140 degrees over 360 degrees. I repeat again, the area of this sector, sector AOB, equals to pi times capital R squared, pi times the radius square. That is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 140 degrees over 360 degrees. So it is pi r squared. The radius of this circle r is 2, therefore r squared is 2 squared, that is 4. So pi r squared is actually 4 pi, that is the area. So 4 pi square units is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 140 degrees over 360 degrees. The value of this expression in total, it is equal to 4.888 square units. In conclusion, found out that the area of this sector, sector AOB, equals to 4.888 square units. So the area of quadrilateral AOB minus the area of this sector will give us exactly the area of this green shape. Okay? So the area of the green shape equals to the area of quadrilateral AOBP, that is 11 square units, minus the area of this sector, sector AOB, that is 4.888 square units. 11 minus 4.888 is 6.111 square units. In conclusion, found out that the area of this green shape is equals to 6.111 square units. Okay, thank you very much.